Hi, Samuel.
Hey, and one of the things I loved that I thought, oh, this is such a fascinating just anecdote that I did not know and was surprising is I thought, people who know Berkeley know that Berkeley had this interpretation, of SES pericope that everything that exists is being perceived, which I would have thought had nothing to do with serious interpretations of quantum mechanics. And then I was very struck by Einstein's question that you mentioned and take very seriously, where Einstein asked in kind of incredulity towards kind of the interpretations being given of what was being discovered through the math. Well, is the moon there if you're not looking at it? And I thought as a writer that I loved the way you used that. So I thought maybe as a prompt, could you sort of explain why would Einstein ask in the context of quantum mechanics if the moon was still there if it's not being looked at? And then your answer you give, I thought, is so profound about how it sort of it's always being observed. And you mentioned the photons, but I thought if that works as a prompt, I would love for you to kind of get into like why would Einstein have said that there's that level of perplexity about what quantum mechanics could mean, that it could somehow seem that absurd even to someone of Einstein's level, or not if you like Berkeley absurd, but obviously Einstein, is implying this is a ridiculous view because of how much it seems to make things dependent in the wrong direction.
Yeah. Well, I mean, that remark arose out of the classic Einstein Bohr debate. So Niels Bohr being, someone who had a different view from Einstein of quantum mechanics. Now, Einstein had the view that actually, strangely enough, despite everything, a lot of physicists, possibly the majority of physicists today, still believe. They're all they're not all, but a lot of them are realists in the sense that they figure there has to be an objective world out there, irrespective of whether it's being observed or measured or however we want to talk about it. There has to be something out there. It can't all be solipsistic. It can't all be, somehow brought into being by our observation, let alone anything else. If that's the case, what happened before there were humans? Surely there is a universe before humans, and it's meaningful to talk about it and so on. So this was his view, and before quantum mechanics, it went aside from philosophers like Berkeley, it went sort of uncontested, because it just seems common sense that should be so. But what quantum mechanics seemed to be showing, certainly to people like Niels Bohr and Werner Heisenberg, is that you can't take that for granted in the following sense, that they would say, or certainly Bohr would say, as far as it's possible to reproduce what Bohr would say, because it's often very hard to figure out what he was saying, but he seemed to be saying that until we make a measurement on a quantum system, and really that sort of means in effect anything, because fundamentally everything is quantum, until we make a measurement of it, until we make an observation of it, the right way to put it is, and I think this is how Bohr would have put it, is we are not permitted to say anything about it, about what it is like, what properties it has, what degree of ontological reality it has. We simply cannot talk about it until we've measured it. And this is what so many people still find objectionable, and what Einstein found so objectionable. But it does seem to be what quantum mechanics, as it's presented to us, is saying, because you find that, for example, the fact that you can put a quantum particle in a superposition of states, this is often sort of talked about wrongly. What people normally say in a situation like that, and if we think of it as being like a quantum bit in a quantum computer, which is basically like a 1 or a 0. So some quantum object that could be in a state of 1 or 0, or pointing up or pointing down. So never mind the details, those are the possible states. And it's possible, quantum mechanics showed, to put an object like that in a superposition where you cannot say if it is up or down until you make a measurement. Then you find that it's either one thing or the other. And the way that's often talked about is, well, it's sort of a bit of both until we measure it. But Niels Bohr would have said, you can't say anything about what it's like until we measure it. And you only get, if you like, you only get an aspect of reality something that we can say, this is how it is, this is what happened. You only get that when you make an observation. So he seemed to people like Einstein to be saying there is no reality beyond what we can observe or measure. And that was really what Einstein's outburst was getting at. Surely this can't be true of something like the moon, that we turn our back on it and somehow it no longer has reality, and then it reappears or reemerges in reality, really, if we look at it again. I think, well, certainly in terms of an object like the moon, or an object, any sort of everyday object, a teacup like I've got here, that I think one can make one can sort of explain how it is meaningful to think about it as having some reality outside of my looking at it, because the reality of it comes from its interactions with its environment. It's only through you could say it's only through those that we can know it's there. It's only because light is scattering off it that I can know it's there. It's only because of the electromagnetic interactions with my fingers that I can feel it's there, and so on. So it has to be an interaction that sort of conjures its manifestation up. But Bohr was sort of going further than that. He wasn't just saying, well, we actually don't know anything about the properties it has until we look. He's saying those properties do not meaningfully exist until we look. And that is certainly true of quantum objects. But in a sense, by this notion of measurement, what that really seems to mean in quantum mechanics is, the best way I can put it, is information about that object leaking out into its environment. So, with this teacup, that information is leaking out all the time because photons of light are bouncing off it, whether or not they meet my eye or not. Potentially, they're out there. They have that information encoded within them. All I have to do is move my head to catch some of them, and then I can see it. So that's really what seems to be sort of fundamental about this notion of what is real or not in quantum mechanics, that its interactions with the environment, that if it, in a sense, sort of crystallize the possibilities that exist in the quantum state, crystallize them into something definite. And that is happening all the time for any sort of large scale macroscopic object. But for a quantum object, you can imagine a situation, and you can create a situation where you can isolate it enough from any interactions with its environment that you're not able to say that. You're not able to ascribe to it certain properties or reality. So in a sense, I would say the sort of resolution of that is, the moon is always, in a sense, out there because there's always sunlight bouncing off it. It's all, for one thing, there are, meteorites crashing into it. For another thing, there are interactions with its environment. But for quantum objects that are sort of fundamentally quantum, that are small enough or isolated enough from their surroundings, that's not necessarily the case anymore. And in that sort of case, it really does seem to be a conundrum that Einstein has raised of whether we can sort of meaningfully talk about the existence of these objects, or at least the existence of their properties, unless we measure them.
All right, that's extremely helpful. So I want to touch on, you talked about you getting to contextuality with the last part of the point, but I want to just go back a bit to the indeterminacy, because I thought, just to ask a follow-up connected to this,
Well, this all makes me think how Bohr said we are lost in words, or suspended in words, or suspended in language. And that to a lot of people that sort of comes across as, oh, it's really hard to sort of say what we mean in these things. But actually, he, as it was usually the case, I think he was more profound than that he was actually recognizing that it's really difficult to find the right word to pin down the concepts that we're talking about. My knowledge of Hegel is not sufficient to know what those right words are. And certainly my knowledge of German isn't sufficient, but it is clear to me that actually finding the right word and the right translation from German is far from trivial. Normally we actually talk about Heisenberg's principle as uncertainty, which is a terrible word to use in that situation. It just seems to imply when we don't really know, there's ignorance involved. Right. Whereas it's nothing. I mean, that's the crucial thing to recognize. All of these terms have nothing to do with ignorance. It's not that there is something that we don't know about. It's that until we ask, there is nothing to be, not that there's nothing to be known. Even that is not quite right. It's that we don't know which of the possibilities will be realized. So it's not as though anything goes. That's often also the implication of calling it uncertainty. There might be anything down there. We just don't know what it is. No, it's really that there are various possibilities, and quantum mechanics tells us precisely what those possibilities are. But it doesn't tell us which ones, in general, which ones we will measure. It doesn't it doesn't tell us. Those they aren't specified. And the thing that really seems puzzling is not just that, okay, then we look and we happen to find, it just pops out that it's this rather than that. It's even stranger than that, really, because what pops out, there is some dependence on how we choose to look. And this is the really perplexing thing, the really troubling thing, actually, to a lot of physicists, because it seems to invoke some element of choice on the part of the observer. It seems to, it seemed then to obliterate the notion of objectivity. But quantum mechanics really does seem to be of that nature. So, for example, if we might have a quantum system that if we do one experiment on it to measure a property, we'll get one result. If we do a different experiment to measure that same property, we'll get a different result. So which of them is right? Well, the fact is that both of them seem to be right, because you cannot think about what property that object has without reference to how you're measuring it, without reference to the wider system in which it's embedded. This is really the sort of fundamental thing that Bohr was getting at. And that, is really the right way also to think about the issue of the moon. That it's not that there's nothing there until we look, there's something there, but the manner of our looking will determine what it is that sort of manifests as an aspect of reality. So, this is the really troubling thing. And it sort of goes, even in this kind of seemingly subjective aspect of quantum mechanics goes even beyond that, in that it seems that there are some situations where it is possible for two different observers to look in the same way at a particular object and each measure different results for this same thing. And that it's not possible, it's not meaningful, in fact, to say which of them is right. They're both right from their own perspective. There is an observer, a perspectival dependence on the answer that you get. So, this is, it just seems irrefutable if quantum mechanics is telling, if it's to be believed, if we take it at face value, if there's not something else that we're missing, it seems to be inescapable that there is this aspect to it, this perspectival aspect and this contextual aspect. It depends what questions we ask. And I think that to me seems to be, in a sense, the more fundamental and the more deeply challenging thing than the fact that we can put things in superpositions and that you sort of might get this answer, you might get that answer. It's the fact that the observer has apparently some say in what we find that really seems so troubling. And I mean, coming back to the links to philosophical ideas, that's why there is a group of quantum theorists who are interested in phenomenology, in the William James style phenomenology, where you start from what you observe, you start from the observer. That's in a sense your sort of prior, rather than starting from an objective world out there. And I think it is fair to say that there are some aspects of quantum mechanics that can be more readily understood and more meaningfully tackled from that sort of phenomenological perspective than from the usual approach of science of imagining that there's an objective world that we then go and measure.
Right, and that's connected to kind of your shift where you wanted part of getting beyond weird is you wanted for instead of stuff showing up weird because we're essentially assuming a kind of classical philosophical background to our physics, which is to do with, well, there's an isness out there. You want to flip it and no, it's fundamentally, it's ifness. What's out there are answers, which means they only exist two questions. And as you stressed in the last interview, you said we can ask more questions, it seems, than nature can give us, at least at any one time, which then shifts everything from the sort of basic question of science is giving us kind of fundamental ontology, maybe, to science is giving us answers to questions we ask. And in giving us those answers, it's told us if we think of objectivity a certain way, we're going to lose it. And indeed, I thought that's a good connection to what you do in your analysis of the object itself. Objectivity is actually a philosophical concept of what an object is, which quantum mechanics shows scientifically is philosophical, not scientific. Because the argument, that you make is instead of seeing just like with the superpositions, which is what I kind of thought, it's like, oh, it's like two things at once, or it's like, no, it's really that until you ask, you can't say. That's the linguistic discipline. I take it first, that we have to have this linguistic discipline about until you ask, you have to recognize you don't know, but you do know very precisely if you ask. You can then stipulate under certain conditions exactly what you'll get. And then if you ask enough times, you'll get the statistical sort of exactly what you'd expect in that distribution of the wavelength. But then if the asking itself is what's worrying people, then they're obviously already worried about non-locality, because that, as you explained it, non-locality isn't about an object being, again, in two places at once. And I thought it was really helpful the way you sort of connected entanglement as a kind of another kind of superposition conception. I thought that was extremely useful for me. It's really useful. So it's kind of like you want to see the same thing. No, it's not two things at once. It's what an object is not what we thought it was. We thought objects had to have properties that adhered in place. And we thought them having a place meant that they were sort of spatially determinate and stable. But it appears that because of, say, if you have two entangled photons, you don't have a single spatially determinate stable object with a complete and invariant set of properties. You have a kind of complex entangled state in which you have the quantum discord, where in order to determine the full set of properties about the quantum object, you must make reference to two distinct objects or their properties that are in relationship to each other. Is that a fair?
Yes. Yeah. I think that's right. And but I guess it's probably also worth stressing that, the quantum world seems to have this nature. We also have a fairly good, if not complete, understanding of why that nature of objects seems to be different when they get bigger, when they get classical. That somehow there is a sort of condensing, you could say, of objectness that happens when they get bigger. And it is absolutely to do with the way that the interactions with the environment, you could say, I think, compel a sort of objectness, a sort of a definiteness on those possibilities.
Yes, can you say more about that? Yeah, talk about decoherence and that kind of transition as you explained, because I think that is really beautiful about showing how sort of you can see the classical world emerging out of this process.
Sorry. Okay. Yes. So how we get decoherence. So I think that this is the aspect of quantum mechanics that has really sort of moved things on since the 1970s. Really, this picture has sort of emerged, and it's moved things on from that old Einstein-Bohr debate.
It was mind-blowing just as a reader who only knew the kind of popular material. This part of the book, especially, I thought was just thrilling.
Right. Well, that's great to hear, because I think that is absolutely the what we sort of tend to hear is still the sort of old stories, and now we can tell a better story about, in particular, about why the world is the way we see it, rather than the way quantum mechanics sort of portrays it. So it is this really. I sort of see decoherence in some ways. It's a bit like an actual theory of what we mean by measurement. Now that's probably going a bit too far. We don't have a full understanding of what measurement really is, but it's not this mysterious term that it used to be, and that it still was really for Bohr. That we can actually sort of quantify in some ways, what is going on when we make a measurement on a quantum object. And it's really a theory of how information about it's a theory both of how the probabilities become actualities, and about how the information that is in the system gets out into the environment. And those two things go hand in hand. The way that happens is by the interaction of the quantum object with the things around it. And you can describe that by quantum mechanics. If you start off very, very simply and just imagine, say, an atom with, so it's a quantum object with certain properties, and the environment might be 5 or 6 gas molecules floating around and sometimes colliding with it. Though we can describe to a degree, in a very simplified model of that system, we can describe that quantum mechanically and see what happens, and see how properties in the object kind of get, well, really what happens is that any sort of interaction between that object and something else, a photon or a gas molecule, entangle it. So that this is basically what entanglement sort of entails. It's an interaction between two quantum objects that links them together, so that then their properties are interdependent. And this is, interaction is what does that. So all that's happening, in a sense, when an object interacts with its environment, is that it's becoming entangled with the particles in that environment, whether they're photons or atoms or whatever. And we can make a quantum mechanical description of that process and figure out how that, in a sense, that entanglement. I said that when two objects are entangled, they're no longer distinct objects; they're sort of one. Well, when lots of interactions are happening in a situation like that, the entanglement sort of spreads and it becomes one big sort of composite quantum entity. And in that case, just as with two entangled objects, you can no longer find out everything you want to know about one bit of it, the original quantum object, the original atom, just by looking at that bit. You've got to measure all the other bits as well and put the jigsaw together and figure out, what all the information is sort of spread out. So that's what's happening with entanglement. And and what it essentially means is that information that was originally in the atom, some of that is now in the atoms that have collided with it. It's out in the environment, or the photons that are scattered off it. And so we can get some of that information by measuring them. We don't actually look, and we don't look directly at that object. We look at the photons that are bouncing off it, just like I said with my teacup. So decoherence is sort of that is the term for what is going on in this kind of entanglement with the environment, and it's called decoherence because what it means is that initially, in order for the object to have the object is you can describe it with a wave function, and so there is a certain sort of waviness, if you like, to those properties that sort of is very steady. But once it starts entangling with other things in its environment, that waviness gets a bit more vague, or at least the waviness gets sort of caught up with the waviness in the environment, and you have lots of this waviness is sort of spreading, and and in the process of doing that, it kind of loses its coherence. the sort of ups and downs, if you like, of the various wave functions initially, they're no longer, you can't sort of follow them without looking at the whole thing. If you look at a little bit of it, it just looks kind of random. So that's really what decoherence is. It's not exactly decoherence, it's just a spreading of coherence. That means you can't actually sort of reconstruct what the wave function is like unless you look at essentially all of it. And we can never do that. We can't get all the photons that are bouncing off an object. We just see a few of them. So what that essentially means is that the sort of coherence of the wave function in the original object that was responsible for things like superposition, that is lost, and the superposition disappears. Or, the quantumness really of that object disappears, and it starts to look classical. It starts to just have to have definite values for its properties. So decoherence is what essentially washes away, because it sort of spreads away, diffuses away the quantumness of that object. It diffuses it into the environment. And in doing so, it makes that object behave more classically. It gives it definite properties. And the theory of decoherence, it's even sort of more subtle than that, because it turns out that there are only certain properties of that object, certain aspects of the wave function that can sort of get out in the environment in a way that can be measured. That don't just become sort of incoherent and impossible to measure. There are certain properties that survive because they have certain mathematical aspects to them. It's just a sort of mathematical thing that it turns out that the interactions sort of don't destroy or mess up that property. They just make an identical copy of it, and then another identical copy, and you just get a whole load of identical copies in the environment. And an observer can, if you like, come along and pick up one of those copies and say, aha, now I know what property, or, now I've kind of sort of determined what property that atom has. So, there is a whole theory for not just how the information gets out there, but what kinds of information get out there in a way that can be preserved and measured. And not all of it can be. So this is really the sort of theory of decoherence, and it gives us a kind of a pretty good account, I think, now of how it is that quantum objects, when they have lots of interactions, they start to take on definite values. And the bigger the object is, if you've got a cluster of 50 atoms, there are just more interactions that it has. And so it more quickly decoheres into a definite object, a definite thing in a definite place that you can see. If it's, a billion atoms, if it's something like a bacterium or, something bigger, then that decoherence happens pretty much instantaneously, because there are just so many interactions that it has. And then it looks, essentially all the time like a classical object. So all of that, we now have a pretty good both experimental and theoretical understanding of how it is that the quantum becomes classical, and why in doing so certain properties become real, if you like. They become measurable. They become things like mass and charge and so on can be measurable, but some other things don't. So there's no macroscopic equivalent of quantum spin, for example.
Right. And so you use that to explain, you mentioned the theory of measurement, and this I thought was extremely subtle and interesting, so I hope you could say more about it, that at the level of the quantum, when you do a measurement, and you think of the measurement in a sense, in the book, you argue it's a kind of information transfer, or almost you could say an information subtraction, because it has as a correlate.